All right. Thank you so much to Lori and the San Francisco Public Library for inviting me and allowing me to speak with you on weather forecasting, essentially just demystifying, how meteorologists predict the weather. My name is Katie Carmichael, and as Lori mentioned, I am a professor of geography at College of Alameda. I also, before we jump into this, want to just give a quick shout out and say happy September equinox. It's not every day that I get to sort of discuss the weather and discuss meteorology on kind of a significant, solstice or equinox event. So I thought that was worth mentioning. This is obviously, the first day of our fall season. If you happen to be in the northern hemisphere, if you're in the southern hemisphere, then this is the first day of the spring season. All right. So before we sort of jump into things, I wanted to give you sort of an outline and kind of a list of the objectives of this, presentation, some of the major sections and goals. So the first is going to be just, a general overview of the field and the study of meteorology. It's important to understand, the science behind it and the scope of meteorology, some of the historical context, and then we'll also get into some of the elements of, modern weather forecasting. Then the next section is on data collection, processing, and interpretation. So my goal for this is for you to become familiar with the sources of meteorological data, data processing techniques, and then also the interpretation of what you'll see as complex data. The third section deals with some of the tools and techniques in modern forecasting. The goal here is to become familiar with the technological innovations and some of the visualization, tools that are used by meteorologists to communicate weather forecasts to each other and then also to you and I as the public. The next section is why we get it wrong. Because as I'm sure you know, our weather predictions and our weather forecasting is not 100% accurate. So I think it's important for this section to understand, some of the reliability issues and the limitations of weather forecasts and weather forecasting. Second to last section is going to be on the future of weather forecasting. So helping you to become familiar with some of the recent innovations and sort of the role that public engagement plays within weather forecasting. And then last but not least, just rounding out by some closing remarks and then leaving it open for, our question and answer portion. All right. So thinking about, meteorology, the science of meteorology and the scope of meteorology. Put simply, meteorology is just the science of weather. I've got the more official, longer definition there. Meteorology is the scientific study of the atmosphere, focusing on weather processes and phenomena. It encompasses the analysis of atmospheric conditions that lead to various weather processes and events. So again, put simply, just the science of weather. And as you can imagine, studying the atmosphere is extraordinarily, vast and complex. And so what's had to happen or what's needed to happen is the field of meteorology has been broken down into sort of branches or subfields, which are listed there. And I'll talk about in a second here. The first one there is what's known as synoptic meteorology, and that field, or I should say that subfield, focuses specifically on large-scale weather systems and their evolution over time. So that would include things like El Nino, La Nina, those major events and things like that. The next branch there listed is climatology. Climatology arguably is sort of branching off into its own separate major field of study. But for our intents and purposes, and particularly in higher education, you'll still see it found within, the branch of meteorology. So for climatology, that is the study of long-term weather patterns. So all of the temperature data that we're collecting, the pressure, the humidity, all of that, taking a look at those long-term trends and patterns that we're seeing. And that obviously helps us to understand, the climate of an area, how that climate is changing, and then some of that variability. The third there is known as dynamic meteorology. So that analyzes the physics and the mathematics that govern our atmospheric motion, things like thermodynamics. And you'll see that when we talk about some of the equations and modeling in a few slides here. The last one there is applied meteorology. So that involves the more practical applications of meteorological knowledge. So that would be in various fields like agriculture, in aviation, and environmental science, to give a few examples. And as you're kind of seeing some of these branches and the scope of meteorology, I think it's important to highlight and emphasize how interdisciplinary this field is. So, for example, the things that we study within meteorology, sort of blend in and evolve with other fields of study, such as oceanography or my field, geography, and also environmental science, and the list goes on. And these disciplines really, work together to enhance our understanding of both weather and climate. All right. So a little bit of historical context, because I think it's important to kind of understand, how things have looked in the past and how things have transitioned into the modern forecasting that we see now and that we use and understand. So early weather forecasting has obviously been incredibly important to civilizations for thousands of years. Even with the more modern invention of agriculture, knowing things like and being able to predict severe weather, predict flooding events, all of those have had, tremendous impacts on humans throughout history, throughout ancient civilizations as well. And the methods for predicting weather have varied, obviously across time and across space. When we take a look at ancient civilizations, we see a lot of the use of natural signs, things like looking at animal behavior. That might be, animal migration or bird migration patterns. That might be taking a look at specific movements associated with individual animals that folks are seeing, restlessness, things like that could give some indication of, a weather event or weather processes that are changing. Along those same lines, becoming very, very familiar with, plant growth and vegetation sort of behavior and adaptations. As we know, being able to sort of understand the weather is extremely important to agriculture, when to plant things, when to irrigate, when to harvest. Those have obviously become increasingly important as we become, settled and less migratory. For many cultures, weather forecasting has become associated with, religion and spirituality. Events such as rain, drought, wind, cloudiness were often associated with a deity or god, and these were worshipped in order to ensure, fair or favorable or just good weather. Rain gods and goddesses were particularly important because rain obviously heavily influences our experience on this planet, not just our agriculture, but everything from that to construction projects and so on and so forth. And we see a lot of this represented, across the globe. Ancient civilizations such as the Aztec, Egyptian, going to India, Norse, Greek, Yoruba, and West Africa, Babylonians, Chinese. There were so many examples of ancient civilizations, you know, attempting to understand and understanding the weather around them. Fast forwarding a little bit, he's considered sort of the modern, how do I want to say this? One of the forefathers of meteorology, and that is Greek philosopher Aristotle. Um, he was one of the first who wrote down some of his theories surrounding meteorology. He wrote what's known as Meteorologica. That was around 340 BC. And that detailed his theories about weather formation, things like, how rain comes to be, how clouds form, wind, so on and so forth. And this is considered a very important text, especially at the time. This was a 4-volume text. And it was considered to be the authority by many on weather theory and weather processes for almost 2,000 years. It turns out a lot of the theories were incorrect, but and inaccurate, but I think it does show just this clear, need and this clear interest in the role that weather and weather science plays in our lives. Let's see. All right. So, getting into a little bit more modern technologies. So, we've had some phenomenal advancements in technology, in standardization, and communication beginning at about the 17th century. And I just kind of summarized some of the main ones, going from the 17th century all the way to, the more modern weather forecasting processes that we have now. Um, the big things that happened in the 17th century was sort of the invention and the distribution of some of our more, how do I want to say this? Our simple weather tools. So that was the invention of the thermometer, which obviously measures temperature. You've got the barometer, which measures atmospheric pressure. Um, and before that, you didn't have that numerical value tied to temperature values or tied to pressure values. Then getting into the 18th century, you have Sir Isaac Newton, and he publishes, his theories on gravity, on motion, and on thermodynamics. And these principles were essential in guiding the science of meteorology into sort of the modern age. Scientists were now able to, use those theories to predict things like pressure systems. You may have heard on the local news where they talk about, oh, we've got this ridge of high pressure coming into our area, and then here's some low pressure coming in. Um, we now know what those mean thanks to, these early theories. So we're able to explain that, how pressure and air move, how they work, and how they create these larger scale systems that could eventually lead to more intense weather like thunderstorms and, tornadoes and hurricanes. We could also explain, just some general weather events, things like storm surges, things like floods, so on and so forth. And then in the 19th century, first up, you had the establishment of meteorological organizations. One of the big ones is the Meteorological Office in the UK. And you also had the focus on standardizing weather observations and weather observation methods. Next there, you have the introduction of the telegraph, and this was key in communication. This enabled for the first time, real-time data sharing, and it eventually led to the first weather maps being created. The telegraph obviously allowed for, the rapid collection of data across large distances, and like I said, led to our weather maps. Let's see. So since the late 1930s, one of the main tools for observing sort of our general conditions within the atmosphere has been the radiosonde. And that is a device. It's a small, expendable, battery-powered instrument package, and it typically weighs about a tenth of a pound up to maybe a quarter of a pound. And that's what we attach to our weather balloons. And so we will send this balloon up with this radiosonde attached. And it transmits, data in real time to an on-ground receiver. And that was huge for getting data across, space and getting data on a regular scale. Let's see, they also transmit their GPS position, and they can go anywhere, they're measuring from the ground all the way up to 100,000 feet. And they last about 2 hours roughly. Especially the modern ones can go a little bit longer. We send those up 2 times a day now on 12-hour intervals, excuse me. And we have about 90 weather stations that release these all across the country. And I've got a map coming up in a little bit that shows you where the closest one to us is here in the Bay Area. But again, that was huge with getting, real temporal, excuse me, weather data and looking at, higher in our atmospheric column, not just looking at data at the surface, but being able to see what's going on, with the jet streams that are traveling above us. And then in the 20th century, you've got a few things happening. This is where you get sort of the eruption of, technology. You get the rise of computers. You get the rise of, weather prediction models, which have significantly improved, the accuracy of our weather forecasts. First up, you've got the role of radar technology, and that was initially developed in World War II, which helped, spot enemy aircraft. But this revolutionized weather monitoring and forecasting. You also have the introduction of weather prediction models, which we are still using greatly today. That began in, the 1950s. Um, and then along those lines, you also have satellite and satellite systems that were first launched in the 1960s. Those provide critical data on cloud cover, on atmospheric conditions, from space. And then last but not least, you've got our modern computing, our advancements in computing power, which have transformed, our models in terms of their complexity, in terms of their accuracy. And it really allows meteorologists to now simulate and predict, weather systems more effectively and more accurately. All right, so sort of looking at our modern weather forecasting. Before we go any further, I think it's important to kind of know the elements that go into, our weather forecast. This typically includes the first six things that are listed there. So the first one is temperature. Generally, you will have a report on the current and expected high and low temperatures for the day. You may also get information on what's known as the sensible temperature, which is how the temperature feels to our bodies. So that would take into account things like cloud cover, things like wind, because you can have, for example, an 80-degree day, but if you've got winds blowing and high cloud cover, then the sensible temperature may feel like it's 75 degrees. So that may be included as well. The next step there is atmospheric pressure. So that is just the weight or the force of, the molecules in our atmosphere pressing down and pushing on, a surface at a given location. Atmospheric pressure is essential in understanding weather. If you know whether or not the pressure in your area is either higher pressure or lower pressure, that can tell you a tremendous amount about what the day-to-day weather is going to be like. So for example, if you have high pressure in your region, then generally that results in pretty fair weather. Whereas if you have a low pressure system coming into your area, then that's where we can get, things like clouds, precipitation, and even more intense things like cyclones, hurricanes, tornadoes, thunderstorms, those types of things. The next there is wind speed and direction, pretty self-explanatory. That's usually expressed as a compass direction and miles per hour. And wind is simply the movement of air. And I should sort of tie that into pressure too as well. So anytime, you feel the wind or the breeze, blowing across your face or you see it moving outside, all that air is doing is moving from different areas of pressure, from areas of high pressure to areas of low pressure. So when you feel wind, all you're feeling is that movement. Next up there is humidity. So that refers to the amount of moisture in the air, and that's often expressed as a percentage. Below that is the precipitation type and amount, if precipitation is expected, and then what type of precipitation that might be, whether it's rain or snow or sleet or hail, so on and so forth. The sixth one there is cloud cover. That's usually expressed as a percentage, of how much of the sky is covered in clouds. This also may involve an analysis of the cloud type, because if you've ever looked at clouds, you'll notice that they often take on different shapes, different forms, and that can actually tell us a lot about how the winds are moving, if precipitation is present, that type of thing. And then at the bottom, I did want to mention, so nowadays, because we have access to all of this data, you may also see information in your weather forecast on visibility, and that's usually expressed in miles, and that tells you how far away you can clearly see objects, things like buildings or hills. It's basically a measure of the transparency of the air. And it doesn't take into account things like, sunlight or the presence of obstructions. And visibility at or above 6 miles is considered clear. The other thing that may be included in a weather forecast is the duration of sunlight, again, when the sun rises, when it sets, and also UV strength, which is known as the UV index. And then last but not least, especially more recently, you may or may not see information on air quality data as well. This is particularly important if we have wildfire situations, like what we've been seeing more and more frequently. There may be information on the air quality and also suggestions if the air quality is particularly unfavorable. All right. So now that we've gone over, some of the history, kind of where we started a little bit, what a general forecast looks like now, let's talk about how we sort of get to that point. So in the next few slides, I talk about data collection and interpretation, and I start off by talking about some of the sources of our meteorological data. The first one up here, these are no particular order, but the first one is satellite observations. So satellite observations capture images of, everything from cloud cover to surface temperatures to humidity to the composition of our atmosphere, what those gases are. They also play a critical role in severe weather tracking, such as hurricanes and hurricane events. Very crucial for storm development and storm movement. And I thought it was worth mentioning, we do have different types of satellites. We have what are known as geostationary satellites, and those provide continuous coverage of the same area. And those are really essential for monitoring weather systems in real time. And one of the best examples of that is our GOES, G-O-E-S, satellite system. This stands for, Geostationary Operation Environmental Satellites. NOAA, our National Oceanic and Atmospheric Administration, there we go, in the United States is the foremost body for gathering, weather data at the federal level. And then our National Weather Service is a branch of NOAA, of our National Oceanic and Atmospheric Administration. Our GOES system, GOES, was a combined project between NOAA and NASA. And it's considered the most sophisticated weather observing, and environmental monitoring system in the Western Hemisphere. It provides extremely advanced imagery and atmospheric measurements. And a fun fact is that it orbits about 22,000 miles above our heads. There are several satellites that are part of this GOES system. There's 4 that are the most recent ones that are operating right now. They start off with letter numbering when they launch them, and then once they get into orbit, they change them into a numeric value. So for example, the first satellite in the series was known as GOES, GOES-R. And then once it got into orbit, now it's known as GOES 16, and that was launched in 2016. We have a GOES 17, a GOES 18, and the most recent one, GOES 19, was launched in June of this year, and it made it into orbit in July. So we've got some really, really recent satellites going up as part of this system. Let's see. The next point there, so the other type of satellite are known as polar orbiting satellites. So these collect data as they pass over the Earth, and they provide global coverage and detailed atmospheric profiles. There are a couple examples that I mentioned there. The first one is NOAA's Polar Orbiting Environmental Satellites, also known as POES. And then also the European Organization for Exploitation of Meteorological Satellites, or EUMSAT, is the European counterpart. And these two systems actually work together. POES makes about 14 nearly polar-to-polar orbits per day, it's sitting about 520 miles above the surface of the Earth. But these two systems actually have partnered together, so they actually provide 2 complete views of weather around the world each day. And they have very sophisticated instruments that provide, visible images, from the visible spectrum of light, infrared imagery, and then also microwave data, which is useful in measuring things like atmospheric temperature and precipitation. And all of that information is really helpful in monitoring, cloud cover, precipitation, surface properties, things like, our ocean temperature and volcanic eruption monitoring and forest fire detection, and even analyzing global vegetation, and also gathering data on, humidity and things like that. So those are a very key part of where our meteorological data comes from. The other, or I should say another, is our radar systems. So these are used particularly for short-term forecasting, and they're very beneficial for severe weather tracking, tracking storm systems, and they are really good at providing, the real-time radar data for things like immediate updates or any sort of fast-moving, developing weather phenomenon. There are different types of radar. The one that we use a lot here in California is the Doppler radar. There are 159 of these radar towers across the US. There's a picture of one up there. That was the first one back in the 1970s. They look like golf balls pretty much. They haven't changed too much as far as their appearance goes. The Doppler radar is really effective in measuring the velocity or the speed of precipitation particles. And that allows us to not only know, what's going on with the rainfall or whatever type of precipitation it is, but also the wind patterns that may be blowing those around, and the rotation of that storm. Radar detects all types, or I should say the Doppler radar detects all types of precipitation. Again, it also detects the rotation of thunderstorm clouds. It can also detect things like debris during a tornado event. And one great thing about, the Doppler and radar in general is that it is, cloud penetrating. So you don't have to wait, for any sort of clouds to dissipate or a clear sky for it to be used. The second type of radar there is known as dual polarization radar. And just like that kind of sounds, you've got, instead of sending out, a specific signal, you have both horizontal and vertical signals being sent out. So it basically enhances and tells us more about the precipitation type, and is key for identifying, the difference between rain or snow or sleet in an area, by looking at how those signals behave as they're being sent out. So that's another key piece of data. So I mentioned these already, these radiosondes. So these are our primary source still to this day for upper air data. There's a picture of them there on the left. Like I said, they're not very large. There's a pen there for scale. As I mentioned, we operate these now twice per day on 12-hour intervals. And these are what we tie to the weather balloons that go out for about 2 hours. And we've got 92 locations across the United States where we launch those weather balloons and connect or collect that data. Let's see, let me show you this picture here. So this one is showing you those locations where we do our weather balloon launches. And the closest one to us in the Bay Area is in Oakland, somewhere near the Oakland airport. The exact location is not privy to the public, but somewhere near the Oakland airport. So if you ever see one of those or come across them, that is what that is, launching from that region. And I've got a link there if you want to see this map more closely. And then it also shows the locations in Alaska and Hawaii and our territories as well. All right, so a couple other major sources of data. You've got our weather stations. So these, when you think about weather stations, excuse me, it's important to think of them as like a network, because these certainly work together. These are, our ground-based or our surface automated or unmanned, oftentimes stations where we are collecting continuous data on, on the ground temperature data, pressure, humidity, all of those things. And these weather stations are really crucial, and they play a critical role in remote areas. being able to access regions where it would be very hard to trek in and trek out on a consistent basis. We're able to set these up, have them, automated or unmanned, and then record that data. It's also important to note that these can be out in the middle of the ocean on ships and on buoys to capture the conditions. Since 70% of our surface is ocean water, that's obviously very important that we do capture our weather data out there as well. The next there is you have what's known as our ASOS, which stands for our Automated Surface Observing Systems. So this is a program that's a joint effort between the National Weather Service, also the FAA, which is our Federal Aviation Administration, and the DoD, which is our Department of Defense. And the primary goal for this is safety and support of aviation operations, but they do collect as a result a ton of meteorological data, hydrological data, climatological, there we go, research information, and then that is shared with the National Weather Service as well. So that is another important source of our meteorological data. Okay, so now that you have a sense of, where all this data is coming from, there's a ton of it. Now let's talk about what happens to it. So we have to have some way of processing all of this information. And so what we end up doing today is we basically assimilate that data into models. And that's basically where we use machine learning and artificial intelligence and other tools to analyze that data, plug it in, and then make predictions for future outcomes. And the one that we use primarily here in the United States is known as numerical weather prediction, or NWP. And that refers to essentially a computer simulation that uses mathematical equations of atmospheric conditions and the ocean environment to predict weather based on, the current conditions that are being input into the system. It uses very, very complex equations. I didn't want to put too many examples of them in here, but things like taking a look at thermodynamics and the laws of thermodynamics, all of that gets plugged into a mathematical equation, and then we can apply it to the weather situations that we're seeing. Let's see. The other thing that's really critical about numerical weather predictions is they allow us to simulate the weather, multiple times. So it's not like we can just plug this data in, run it one time, and then that's our output. We are able to kind of get a broad range of what maybe the best case versus worst case scenarios might be if we're dealing with some kind of extreme weather event, which really helps with accuracy. And then we can also look at things over time, right? So you're getting detailed forecasts ranging from not only just hours but also potentially weeks ahead. All right. The other thing that I wanted to just mention briefly with these models, we do have global models versus regional models. So some of our numerical weather prediction models can take a look at global scale things like larger atmospheric trends, like jet streams or El Nino or La Nina events. And then we have smaller scale regional models. And that's where we can take a look at things more on a localized level. Which may be important if you're looking at, a specific urban area and the weather conditions that are happening in that region. All right, so the basic process for, taking this data is I kind of simplified it into this sort of three-step process. So once we have, that data, we put it into, our model and we get that output. And one key thing with the modeling is that, meteorologists do have to interpret, not only the data that's being produced and being plugged into the model, but also the assessments that are coming out as well. And that's where, sort of having that sort of background and knowing more of the nuances and having that human aspect and that human element to weather forecasting is crucial. Ensuring that what they're seeing in the output is making sense with what's going in. Then you have the step of ensembling, creating the forecasting, or what's known as ensemble forecasting. So that's where you will take that model and you will run it multiple times to capture any potential uncertainty that may be coming out in the predictions. And then also, like I said, providing sort of a range of potential outcomes. And that can help forecasters and local governments and things assess risk and make decisions based on that information. And then sort of the last piece there is considering some of the visual techniques. So now that you've gathered the data, you've input it into the model, you've gotten the forecast. Now it's important to be effective, right, in communicating that information, both to other meteorologists and also to the public as well. So this is where the tools and the software we use to visualize complex meteorological data comes into play. Things like weather maps, which can illustrate various, things from atmospheric pressure to temperature, to other anomalies. You also have to decide if, maybe instead of a weather map, you want to use some other kind of graphic output, right? Maybe you want to take a look at and plot contour, information. Maybe you want to have time series graphs or animations, some other sort of visual aid that will help present this data in a way that clearly provides that forecast information for those that need it. All right. So just a couple of sort of examples of the visualization tools. So I mentioned, the weather maps. That's that first point right there. So our weather mapping software, we do have specialized software that meteorologists use to, use that model data and then, create that weather map output. And usually these can be singular. You could just have a weather map, obviously, on temperature. You can just look at pressure systems or precipitation, or you can expand that out and look at, obviously, larger scale things happening as well. The other big visualization tool nowadays are the interactive dashboards and the applications that we have, and these are just erupting all over the technological landscape. Um, so these interactive dashboards, which are just digital interfaces, obviously allow meteorologists and the public to explore data in real time, to customize views of what they want to see, and then access those localized forecasts. We also have what's known as our Advanced Weather Interactive Processing System, also known as AWIPS. And that is a really important telecommunications system that's basically the cornerstone of the National Weather Service. It's an interactive computer system that basically integrates all of the meteorological and hydrological data with satellite and radar imagery, and helps forecasters, again, sort of prepare those outputs. Um, you also have things like open weather dashboards. IMBD has dashboards and other visualization tools as well. And then you have countless apps that are out there right now. AccuWeather is one of my favorite. You've got just weather apps, weather channel apps, Weather Underground, etc. All of those are sort of key pieces, obviously, in sort of communicating this information. And then down there at the bottom, the last one, part 3, you've got our GIS, our Geographic Information Systems, and that is our mapping software. So we use that obviously a ton within the meteorological, within meteorology, within geography, and within our field. This is where you can take different layers of data and then put them together, analyze them, and then come out with, a finished product. Sorry, you were frozen on my end. Am I still okay? Oh,
I see your modern forecasting slide.
okay, perfect. Sorry, I can hear you. It's just frozen.
Now I see the communication slide.
Okay. Perfect. Thank you. All right. Um, So once you have all this information, the key element is, communicating this information to the public, right? Because you can have the most wonderful forecasts and, the most wonderful predictions, but if they aren't getting out there to whoever needs them, then it's worthless, right? So communication is such a key aspect of weather forecasting. And communication in particular with public safety and management, with local governments, being able to communicate severe weather, like what you're seeing in that picture over there on the right, that screenshot. And as an example, we have our wireless emergency alerts system, our WEA, which does obviously notify via text. That's our federal emergency system. It does notify folks if there is, an emerging threat in their region. All right. So why do we get it wrong? Oops. There we go. So generally speaking, the how do I want to say this? The closer you are into the future, the more accurate your predictions are going to be in terms of forecasting and all of those elements that go into a weather forecast. So, generally speaking, if you're within the first 5 days, the 5 day forecast is considered to be about 90% accurate. When you start getting out to a 7 day forecast, you're looking at about 80% accuracy. And then beyond that, 10 plus days, you're looking at about 50% in terms of accuracy. And there are a number of different reasons for this. I think the biggest to highlight is that, weather is complex. Our atmosphere is so complex. And, having all of this data is wonderful, but oftentimes we still, having the data, it has to be, at the highest quality data that we can have. It also has to be, if you've got gaps in your data, then that's going to throw your model off. If your equations are off, then your model's also going to be off. So ensuring that we have as much data as possible and addressing any gaps in data is crucial in terms of accuracy. The models themselves, too, are not error prone. That's one of the reasons why meteorologists will do a range and, input data into the models and run them several times just to sort of see if there's any uncertainty. Um, all of those factors really sort of, have a play in why we get these inaccuracies. All right, so taking a look at, the future. We've got a number of, innovations, not just on the horizon. A lot of them are here already. There's an eruption in remote sensing technologies, and also drone and unmanned aircraft is a huge part of this. There's always the quest for higher resolution data and higher resolution imagery. That is key when you're looking at any sort of, remote sensing technology is, what's the scale, what's the scope, how close, and how much data can we gather, from these images that we're capturing. We're also seeing a ton of enhanced computer power, with the eruption of, AI as well, kind of leaning into that, and machine learning. All of that has had a tremendous impact on, our weather processes and I should say, our weather forecasting. Um, Looking to the future as well, the role of public engagement is crucial, improving public understanding, supporting initiatives that, help, fund and educate the public on not just things like emergency preparedness, but understanding, general weather processes as well. Incorporating real-time communication. And a big part of that nowadays is social media, and ensuring, that however people are, digesting, their media, digesting whatever it is, however they get, their information from, that the weather forecasts are being incorporated in that as well. And then I did at the very bottom there, I did put a link to our Citizen Weather Observer program, which is something you can check out if you've ever been interested in weather forecasting. What this is like the name suggests, citizens can participate in sending their data to the National Weather Service. So if you happen to have, an at-home weather station, you can connect to the National Weather Service, and the link is there to have your data input as well for your area. All right. And with that, I want to say thank you. Thank you so much for having me. I really want to encourage you if, meteorology and, weather science is something that's of interest, definitely, take the time to look more into it. Obviously, everyone needs a weather forecast, and it's so important, to understand, the meteorological processes that impact our day-to-day lives. And my email address is there as well. If you ever want to reach out to me, I'm happy to answer any questions.
Thank you so much, Katie. I see two questions in the chat um, from Diane. Do you know of any 100% online meteorology programs that are tuition free?
That is a wonderful question. Not off the top of my head, that's 100% online. But if you want to shoot me an email, I can certainly look into it and give you, some names if I find any. Absolutely.
Okay, thank you.
I will say there are very few programs in the United States that offer meteorology as a degree. So we're a little limited as far as that goes. But yeah, feel free to send me an email. I'm happy to answer that better.
Okay, great. Thank you so much, Katie. Um, do you think that AI will take over the job of meteorologist anytime soon? Technology is advancing so fast now.
That's a great question. And it's obviously hard to predict the future. I will say that, we can't replicate how quickly, we can take this data and plug it into these programs and, get, the outputs within, seconds, within minutes. And a lot of this data is coming in every few seconds, especially if there's a severe weather event going on. So there's always going to be a need for um, whether that's artificial intelligence, whether that's, if you just want to call it computer science, there's always going to be a need for us to be able to analyze that data so quickly. Having said that, I, I would be concerned, with just having the computers, run the forecasts by themselves. There's so much nuance and there's so many microclimates and there's just weather is so complicated. And especially now with, the way things are changing, with our larger scale climate, it's just extremely hard to just, plug that data in and say, okay, well, that's got to, that's correct, instead of actually looking at the data and having that, human element and that human observation, um, look at it and analyze it and double check, even so to speak, to make sure that what's being output makes sense.
Okay, thank you, Katie. Question from Larry. I use Weather Underground. Their maps of local station make me think that amateur weather station are in play. Is that correct?
That what's in place? Sorry.
Amateur weather stations.
Oh, yes. So that's huge. Um, I will say that, I mean, I tried to look up how many weather stations exist, and all I got was a list of thousands of different networks, where within those there were thousands, if not hundreds of thousands of individual what are considered weather stations, whether that's, private, citizens collecting that data, amateurs, whatever it is. That's definitely a key part of it. And that's also where some air may come into play as well. But yes, that definitely plays a big role.
Okay. And another question from Diane. What book would you recommend for people interested in becoming meteorologists?
It's a good question. Um, Gosh, I'm trying to think of just one to give you off the top of my head. Do me a favor and send me an email because I've got a list I'm curating as I speak.
Okay.
I would love to send you a bunch of
Yeah.
titles.
Yeah. I'll also look in the catalog. If I find something that the library carries, I'll also send it to her. Let's see. Do meteorologists mainly work from the newsroom in the daily basis, on the daily basis, or do they have to go out to the field to report like news reporters?
That's a great question. And it kind of depends on the network. I would say that most, the folks that you see, on the local news are generally within the newsroom. Um, Having said that, I mean, I have seen some people out and about too, but generally speaking, that's a separate role. Those that would go out and, collect data or, check on weather station data, would be separate from those that are actually, reporting it.
Thank you so much, Katie. That's the last question, but I do see a lot of thank yous in the chat, thanking you for your presentation, your wonderful presentation. Um, so if anybody else have any question, please feel free to enter it in the chat, and I can also allow enabled unmuting so you can unmute yourself. If you have a question that you can ask directly, you can unmute yourself if you want.
Let me share here.
Okay, if we don't have any more questions, I want to thank Katie for your wonderful presentation. Thank you for taking the time to share with us how meteorologists forecast the weather and the science behind predicting the weather. And I also want to thank everyone for joining the program. I hope you all find the presentation interesting, helpful to you. I will send out an evaluation survey together with Katie's presentation slides and a link to today's recording. Please give us your feedback so we can continue to improve. Again, thank you, everyone. Have a wonderful rest of your day. Bye bye now.